Good morning, everyone. Roger Penrose cyclic Big Bang theory. Roger Penrose calls it conformal cyclic cosmology. As per most accepted Big Bang theory, the universe started from nothing. But there are others who don't agree with this idea. They think matter was present from past and there was no start date. There are only two things possible. One, our universe started out from nothing as per Big Bang model, or there was another universe before our universe and Big Bang totally wiped out the previous universe and created our one. As far as Big Bang theory is concerned, it is well accepted today. According to this theory, the whole universe was at zero volume, known as singularity, and then a large explosion happened and the universe was born. As per Roger Penrose, matter was there all along, from eternity, in the past, and will continue to be around till eternity. There is no beginning or end to the universe. He shows evidence and has also formulated a theory known as conformal cyclic cosmology. Unfortunately, it's not accepted by the scientific community, but in my opinion, definitely worthwhile to take a look what he's saying. So let us start. Big Bang. As per mostly accepted theory, there was nothing before the Big Bang. There was no previous universe before the Big Bang. Now, as per Roger Penrose, there were more universes came and went before the Big Bang. Before we talk of Big Bang, let us discuss the size of the universe. How big is the universe? If you were to scale down the sun to a 1-foot diameter soccer ball, in that scale, the nearest star would be 5,000 miles away. In other words, whole of Asia would be enough only to represent 3 stars. As you could see here, 1, 2, 3. So there are 3 soccer balls in whole of Asia. If you scale the size of the sun to a soccer ball, and you could see how far apart these stars are located. See the 3 black dots to represent 3 soccer balls. The black dots are not to scale. Our galaxy with 400 billion stars would stretch beyond Mars with that scale. Now let us ask another question. How many stars are there in the visible universe? There is on average approximately 400 billion stars per galaxy. It is estimated there are 2 trillion galaxies in the visible universe. If Mount Everest is made up only with sand grains, we will need 30,000 Mount Everest-like mountains to represent the stars in the visible universe, each sand grain representing a star. That's how many stars are there in the visible universe. So let's go back to Roger Penrose theory. Previous universe before Big Bang. So, as per Big Bang model, we are here at the present, and there was a Big Bang happen, and that's it. There was nothing before that. They don't even question. The reason that the scientists are given is that we don't formulate theory because there is no evidence before the Big Bang. This is the majority scientific view. But Roger Penrose says that there is evidence about a previous universe before the Big Bang. And we will see what evidence he is presenting in this webcast. So according to Roger Penrose, there's the Big Bang and this is our universe. And there's the previous universe, and then here's the previous Big Bang, etc. So infinite number of big bangs and universes came and went as per Penrose. Evidence for previous big bangs and previous universes. Let's see what Roger Penrose giving us as evidence. Roger Penrose asked the question, what can come to our universe from the previous universe? Roger Penrose thinks the biggest explosions in the universe today are crashing of two supermassive black holes. One supermassive black hole is about 1 billion suns to 10 billion suns, in that range. When two of them clashes, large gravitational waves are released. We have detected gravitational waves from black hole clashes that happened 2 billion light years ago away. And these things that we have detected is from our universe. So here we see two supermassive black holes are colliding and the gravitational waves are produced. So let's go here. So our universe is here, and then this is the previous universe, and when they collide, and they would send a gravitational wave, and it would be coming to our universe. It probably came. So how do we know this happened? Let's continue. As per Penrose, collision of supermassive black holes in the previous universe creates immense gravitational waves. These waves will be recorded in cosmic microwave background radiation. What is cosmic microwave background radiation? Cosmic microwave background radiation. Let us imagine a bomb explosion. After a large bomb explosion, there would be smoke and dust in the air. Similarly, Big Bang theory predicted that there would be a microwave background radiation everywhere in the universe due to the Big Bang. The Big Bang theory also predicted the temperature of the cosmic microwave background radiation, let us call it CMB, is 3 Kelvin. This background radiation has been found, and the temperature on the CMB is exactly as predicted as the Big Bang theory. This is a map. The red parts indicate slightly higher temperatures and blue parts indicate slightly lower temperatures. Gravitational waves. Gravitational waves were detected a few years ago. These waves are from our universe, not from the previous universe. So if you drop a stone into a lake, you would see concentric circles. Concentric means each circle has the same center. As per Penrose, we should be able to see concentric circles in the CMB that were created due to collisions of supermassive black holes in the previous universe. I have given the reference here. Wilkinson Microwave Background Probe, WMAP, was used, and some type of computer simulation was done to show that there were concentric circles in the CMB by Roger Penrose. Unfortunately, scientific community has accepted this simulation by Penrose and Garsadian. So what Roger Penrose is saying, let's go back to this map here. He has done some computer simulations, and similarly you do computer simulations on photographs of Earth's surface to find ancient craters. You cannot see from your eyes, but you could look at the elevation difference, and computer can say there is a crater here or crater there. These ancient craters are due to asteroid dropping of asteroids or anything like that. So similar technique was used, and he says there are concentric circles that can be shown mathematically in this cosmic microwave background radiation. And unfortunately, these simulations were not accepted by the majority of the scientific community. So one signal is collision of big bangs, or collision of black holes, and come into our universe and been recorded in the microwave background radiation. And there's another signal from the previous universe that he's coming up with, Hawking points in the CMB. As per Penrose, Hawking points also can be considered to be signals from the past universe. What are the Hawking points? Let us see what will happen in the future to our universe. It is well confirmed that universe is expanding. It is also well confirmed that this expansion is accelerating. In other words, expansion rate is increasing every second that goes by. The expansion of the universe started 13.8 billion years ago, and there was a very brief inflationary period. Some people don't accept the inflationary theories. And then the expansion happened at a steady rate after the inflation. Suddenly around 4 billion years ago, expansion of the universe started to accelerate. This is what we see. There was the Big Bang and then inflation. As I said, inflation is not, some people don't accept that. And then there was a steady expansion of the universe. Probably around 4 billion years ago, it started to accelerate. Expansion started to accelerate. And this is due to dark energy. And dark energy forces gets more powerful when the volume of the universe gets bigger and bigger. Another photograph of the universe is the Big Bang and the expansion and inflationary period, etc. In the distant future, all galaxies will be out of the visible universe. Nearest planet will be billions of light years away. Earth will be broken down into atoms. All matter on Earth will be scattered in a large area. By then all stars have exploded and have converted to dead white dwarfs. All matter starts to decay. Electrons and protons will turn into radiation. This is not confirmed. Finally, black holes would start to vaporize. When a supermassive black hole vaporizes, gravitational waves will be created. These gravitational waves will create an imprint on the CMB of the next universe. Similarly, dying black holes in the past universe would have created an imprint on the CMB. Penrose calls them Hawking points to honor Stephen Hawking. Penrose has written papers showing the existence of Hawking points in the CMB. Unfortunately, not accepted by the scientific community. Now we look at another thing. There's a big entropy problem of the universe. This is like other problems, flatness problem, monopole problem. There are a lot of problems that has not been solved. So we are looking at the entropy problem of the universe. And this ties into our past universe. First, let us look at what entropy is in a very simple manner. Two rooms with gas particles are shown below. Gas particles move around randomly. Room A, gas particles are arranged in a very unorthodox or very special manner. And there's nothing special about this. This is the way gas particles would arrange. So this room is considered to have high entropy. This room considered to have low entropy. It's always go from low entropy to high entropy. It's possible to go from here to here, but the chances are very, very remote. And you could calculate that. There are equations for that and the Boltzmann Equation. Anyway, normal situation is here with high entropy. It's always, mostly, it's from A to B is what you would see happening. There are many ways that gas molecules could arrange. Gas particles room A seems to be concentrated at the middle. Can this happen? Yes. But the probability of this type of arrangement is low. Most likely scenario is room B, where gas particles spread out in a random manner. Gas particles in room B is randomly arranged and there is no order. Gas particles in room A seems to be arranged in a non-random manner centered around the middle. Hence we say entropy in room A is low. Also, it is a special low probability situation which is not a common occurrence. Now let us look at room C. Room C, extremely special situation, very low entropy. This is very low entropy. As you can see, the arrangement of particles are very special. Special means it's not common. It's not a common situation. You don't see particles in a room full of gas molecules being arranged like this. But theoretically it's possible because gas molecules are moving around randomly. It's possible, but there's a probability that it's be very, very low. But it could happen if you wait for millions of years. Now let us look at the present universe. Everywhere we look, entropy seems to be going up. That means we see going from room A to room B, entropy going up. Things are getting scattered. Everywhere we look, entropy seems to be going up in the universe. Gases are spreading out. Increase of entropy with time is known as the second law of thermodynamics. There are other ways you define second law, but this is one way. On the other hand, star formation is an entropy reduction process. Gravity brings particles together. There's gravity that we cannot forget. So in the case of gravity, instead of spreading out, dust and gases would come together and the stars are formed. So in this case, entropy is reduced. One can see that spreading and dispersion of dust and gas makes the entropy to go up, and gravity makes the entropy to go down. Due to expansion of the universe, increase of entropy due to dispersion is much higher than lowering of entropy due to gravity. Now there is another issue to be considered. Gravity also contributes to entropy increase. How does that do? This is due to black hole formation. Large star collapse and create black holes. So when a black hole is created due to gravity, and this has a very high entropy because matter is totally spread out inside, or matter has converted to some kind of a gravitational energy, and that is well spread out. So entropy goes up. Any matter falls to black hole will not come out. Entropy in black holes are given by Birkenstein-Hawking entropy equation. Entropy inside a black hole. C cube AO 4GH. C is speed of light. A is surface area of the black hole. G Newton's gravitational constant. H Planck's constant. Entropy inside all black holes in the universe is 10 to the power 1, 2, 3. Entropy in all other matter is 10 to the power 101. 101 is much smaller number than 10 to the power 1, 2, 3. For an instance, 10 to the power 10 plus 10 to the power 11 is 1.1 times 10 to the power 11. 1.1 10 to the power 11 can be approximately taken as 10 to the power 11. Similarly, 10 to the power 10 plus 10 to the power 15 is 1.0001 10 to the power 15. This is essentially 10 to the power 15. Similarly, 10 to the power 101 plus 10 to the power 123 is essentially 10 to the power 123. So we can say by far the entropy in the universe is contained in black holes. Now let us go back to the second law of thermodynamics again. If the entropy is going up today due to second law of thermodynamics, then entropy has to be very low in the past. So the present entropy is here. Entropy has to be very low at the Big Bang because it has been going up for 13.8 billion years. As shown in above figure, due to second law of thermodynamics, entropy keeps going up. If this is the case, entropy at Big Bang has to be very low. But there's a problem, and that is called this entropy problem. And what is the problem? But the problem is CMB, cosmic microwave background radiation, is a homogeneous soup of radiation. CMB is considered to be emitting a Planck's blackbody radiation. Hence, entropy is at a maximum during CMB. So, due to the CMB radiation, just after the Big Bang, entropy has to be at a maximum, has to be here. If it's at a maximum, then how could it be going up? But if we observe the universe, it is going up. It is going up. So if you go to the Big Bang, it should be low. But the cosmic microwave background radiation says it is not low, it is very high. That problem has not been solved. That's called the entropy problem. CMB data suggests that CMB is basically black body radiation. Hence, entropy at CMB is essentially the theoretical maximum of entropy of the universe. But entropy has been going up from the Big Bang. If the universe started with maximum entropy possible, then how could it keep going up for the last 30.8 billion years? This problem has not been solved by modern science. Entropy of a system is calculated using Boltzmann Equation. Boltzmann Equation is etched in his tombstone. S equals K log W. Let's see what this means. S equals K log W. S is the entropy, K is the Boltzmann constant, W is the phase space that would be possible arrangements of particles. Phase space is the number of possible ways gas particles could arrange. Total entropy in the universe today calculated to be 10 to the power 123. Hence, possible phase space is 10 to the 123 to 10 to the 123. 10 to the power 123 to 10 to the power 123. Twice. This is a huge number. For an example, all the protons and electrons in the universe is only 10 to the power 83. So here 10 to the power 123 times another 10 to the power 123. 10 to the power 10 to the power 123. How did this happen? How did the universe start with such a low entropy that has such a low probability of happening? Roger Penrose has a theory based on Weil tensor. Please check my part 2 for the Weil tensor hypothesis of Roger Penrose. Weil tensor is Hermann Weil, who lived during the time of Einstein, came up with this tensor. Which is a tensor in my part 2 I will explain. Here are the quiz to see whether you listen to this. How many Mount Everest sized mountains are needed to represent all stars in the universe, assuming one star is equal to one sand grain? What evidence Roger Penrose shows to indicate that there was a universe before the present one? Why there is a second law of thermodynamics if the universe has been around for 13.8 billion years? So I hope you would join me to listen to more evidence of Roger Penrose. I put it onto part 2 because it involves little mathematics, but I would say that you should be able to understand most of the stuff. Thanks a lot for listening.